All right, so now I'm going to move to two-dimensional motion. And the two-dimensional motion is a direct application of both the laws that we've studied, namely the horizontal law of inertia and the vertical acceleration equations and behavior that we've calculated. So now this is the combination. And the result of combining the two is that we can now understand why the path of these fountains are parabolic. Okay, so we can understand this beauty of nature as to why it follows this beautiful parabola. And if you remember, I had shown you that Archimedes was the first person who thought about the mathematical curve of the parabola, although he did not apply it to motion of water, and that Da Vinci had shown that the path of water fountains or cannons and so on is in fact a parabola. And so what Galileo did was he first, as I said, he was a very close observer of nature and he made careful measurements. And so his first curiosity was that if you have a beaker of water with a hole in it and the water is falling, this picture is not quite correct because I need a friend here who keeps the water full in the beaker, okay? So somebody is helping him keeping the level at this point, okay? So he saw the water fall and he said, what is this? What is the nature of this trajectory? Is it a cycloid? And what he did was he took his ruler and he measured that if you take distance 1, 2, 3, 4 along the x-axis, what is the distance along the y-axis? And what he found is that for 1 unit here, if the distance is 1, then for 2 units the distance is 4, for 3 units the distance is 9, for 4 units the distance is 16. In other words, the y-axis, the y deflection goes like x squared, and y equals ax squared, y equals a constant times x squared is precisely the equation that describes the parabola. So Galileo literally measured the parabolic path. But now, what was even a bigger accomplishment is Galileo could prove, based on his two laws, that the path has to be parabolic. And in doing that, he then invented a new law, which is very profound. And that profound law is that the horizontal motion of the water or the cannonball and the vertical motion of the water are two independent motions that follow his laws, and they follow those same laws independently of each other. In other words, the horizontal motion doesn't care that it's also falling. It follows the horizontal law, namely the velocity is constant. And the vertical motion doesn't care because it follows the law that, of constant acceleration. And this idea that horizontal motion and vertical motion are independent is a remarkable conclusion which we call the decomposition of motion. And I'm going to show you that with an experiment here, which he realized. I think he was one of the first people to realize that if you launch a cannon, then the cannon will go the cannonball will go a certain distance, and it doesn't matter how much explosive powder you put in the cannon, okay? Clearly the ball will go further if you put more explosive powder in the cannon, but its journey will end in one fixed time, the same time. So the journey of this ball will go either straight down or like this or like that, but the journeys are all the same, namely they go obey the vertical motion. Namely they fall in the same time. And this is what this demonstration will show you here. It's a little hard to see, unfortunately, because these balls are rather small. Okay, so I've got this little tiny steel ball here, so look very closely. I think I've got all the lights on. And I've got over here a cannon, okay, and I'm going to charge it up because I've got a spring here, and then one of these balls has a hole in it, and I'm going to put it through this launcher, and the other ball has no hole in it, and I'm going to set it over here. There's a little dimple here that helps me hold the ball down so it won't fall down. Stay. Okay. Actually, I'm going to, yeah, sorry. All right. So when I release the spring, here's the spring. When I release the spring, this ball is going to go straight down. Whereas this ball is going to be hit by the cannon and it's going to launch. And what you've got to look for is when the two balls hit the ground. Okay? Ready? So we're going to use the law of inertia, which says if you launch a ball with a horizontal speed, it will go on with that horizontal speed forever and ever and ever and ever. Okay? And the other law we're going to use is that when we launch the ball this way, it will fall with acceleration a according to the laws I gave you. So now we're going to combine those two laws, but apply them independently. I'm going to say the vertical motion will take place independently of the horizontal motion. The two don't know what the other guy is doing, and that proves that the path will be a parabola. So again, this derivation is in the appendix. Okay, what we're going to do is we're going to prove that the y-coordinate of the path is related to the x-coordinate by Archimedes' parabola, y equals ax squared, not by literal measurements with a ruler, but by simple mathematics and application of the laws. Okay, now we'll start with the law that the horizontal velocity v that is launched at is a constant. Okay, so if it's a constant, then the distance traveled x equals the velocity times time. Okay, 50 miles per hour times time is 50 times t. So this equation here can then be used to eliminate time. So if we want path, and path is just y and x, and there's no time. So I'm going to use this equation to eliminate time. And now I'll look at the vertical motion. Suppose that the body starts out with an initial vertical velocity 0, then the acceleration due to free fall is due to this constant g, where it's a constant, and the vertical distance traveled is 1/2 at squared, so it's 1/2 gt squared. Now I get rid of t by taking this t and plugging it in here. So y equals 1/2 g x squared over v squared, because that's x over v. Now g is constant and v is constant. Okay? Because this is the law of inertia and this is the law of free fall. So when you apply the law of free fall and the law of inertia together, you get the parabola, because this part is a constant. You get y equals constant times x squared. Okay? That's the equation of the parabola. So both of these quantities are constant. So now it can actually prove mathematically that all of these trajectories that you use are in fact parabolas. Okay? Now this of course gives us a nice opportunity to analyze more complicated motions, like instead of just this simple motion of something falling down, I can actually launch something at a certain speed and a certain angle, and I can calculate this full parabolic trajectory. It involves quite a bit of mathematics, which I won't go through, right? But one of the new ideas that's introduced here is that the velocity or the ball is moving at different speeds. Like when it's up here, but when it's at the top, right? When it's all the way at the top, the ball is not moving up or down at all, because when you throw a ball straight up or down, the ball comes to rest when it reaches its highest point. However, it's still moving horizontally. So you see, the ball is moving horizontally here, okay, and here is a combination of horizontal and vertical. And so when you do the full analysis of these parabolic trajectories, you have to take into account the speed of the ball and the direction, because both are changing. Okay, and that's where you introduce the idea of vectors, which we will not do too much about now, but later on we'll do vectors. Okay, or you can take this motion here and resolve it into two components by drawing a rectangle around it and say this is the vertical component, and then this one is the horizontal component. This component obeys the law of up and down motion, and this component obeys the law of inertia. Okay? And using how these two change, you can calculate the parabolic path. And Galileo did this, and it was not just an academic exercise. It turned out that it had a very important practical application for the ships, because the ships would use cannons to shoot down other ships, right? And the question was, what's the best angle to arrange your cannon in order to hit the ship that's furthest away before it can come close enough to hit you, right? So you want to arrange your cannon so that you can get that ship as far when it's much further away from you. Of course, if he knows the laws of physics, he will choose the same angle and also be able to hit you. So the answer is that if you want to launch a cannon and make it go as far as possible, then you have to choose an angle of 45 degrees. And it turned out that just by trial and error, all the ship pilots and cannon, the military commanders on the ships, they knew this rule. Okay? And Galileo said, from the accounts given by gunners, that's the word I was looking for, gunners, I was already aware of the fact that the use of cannons and mortars for the maximum range, that is the one in which the shot goes the furthest, is obtained when the elevation of the shot is 45 degrees. But to understand why that happened far outweighs the information obtained by testimony or even by repeated experiment. And now that is what I'm going to sort of show you first, is that the behavior of the cannon, when hopefully this one doesn't mess up as much as the other one. Again, I got these tiny ping pong balls, okay, and I've got a cannon over here, which you can see, right? And I'm going to change the angle of launching of this cannon by moving this over here. And right now, I'm going to show you that the furthest travel of the cannonball will be if I choose this angle to be 45 degrees. So right now, do you think it's at 45 degrees? No, this 45 degrees is more like this. This is 0 degrees, this is 45, this is 60, this is 90, right? So if the gunner arranged the cannon to be 90 degrees, what's going to happen? He's going to shoot himself, right? So we won't do that, right? Okay. So if the gunner arranged the cannon to be horizontal, he might think he'd be able to go further, right? But what will happen if he did it horizontal? Let's try that first. What will happen if he did arrange the cannon horizontally, right? Like this. Okay, so I'm going to put this cannonball in here, and what? Okay. Ready? So you see, it didn't go very far because it had a lot of horizontal velocity, but it had no vertical velocity at all. Okay, so it went straight down. Okay, so it didn't spend much time in the air. All right, so I won't do the 90 degrees because that you know the answer to that, right? It's going to destroy itself, right? So now let's choose this angle of 60 degrees. All right, and this is the ball. And if we did our calculations correctly according to Galileo's equations, then it'll land in this bucket here, with this styrofoam in here. Normally I have a student hold this bucket. Usually hits the student in the head. So let's try that and see if it works, okay? I can actually launch this at 30 degrees too, okay? Let me try that 30-degree angle. I think I changed the angle when I did that. Uh-huh. Okay, I got 30 degrees. I should get it approximately right. All right. I almost hit it, right? So 60 degrees and 30 degrees will hit that tray, okay? So now, let me try 45 degrees, which is Galileo's great derivation. Namely, that will give you the maximum range. And okay, I got 45 degrees here. Does that look about symmetric? 45? Yeah, and the ball is already there. I put some cannon fodder. 1, 2, 3. Okay. Now that was, the two experiments were 30 and 60 degrees, okay? So now we're going to try 45 degrees. And it should go way beyond the tray, all right? So the maximum range that you get is when you take the angle of 45 degrees. Now we'll see what Galileo derived, that 45 degrees is the right angle. So basically he said that if you choose a low angle, then the velocity is mostly horizontal, okay, and very little vertical velocity. The vertical component is very small. And since the time that's spent in the air depends on the vertical component, because that's when it goes up and down, that time is very short, and so it won't take advantage of this very large horizontal component. So that's the wrong thing to do. And if you tilt it beyond 45 degrees or too close to vertical, then your vertical velocity is very large. See, the vertical component is very large, but the horizontal component is too small. So yes, the ball will spend a lot of time in the air, but it doesn't have enough oomph to go very far while it's going. So the right thing to do is to do a compromise, a symmetrical compromise between these two, which is exactly 45 degrees, when the time spent is halfway, sort of, and the velocity spent is halfway. So now you've optimized both velocity and time, and now you get a dramatic effect of how far the ball can go. So that's why you get 45 degrees. In fact, those two components have to be equal in order to do it. All right.